Hello everyone. In this video, we are going to see about a functional dependency theory and algorithms for decomposition. So, functional dependencies we had seen in the previous video that how normal form can be implemented by using a functional dependency. Then the given set of functional dependencies, there are certain other functional dependencies that are logically implied by F. For example, if B is functionally depending on A and C is functionally depending on B, it is a transitive dependency we call. See here, C is functional, then C functional depends on A, right? So A, B na determine madidre, B, C na determine madidre, of course A can determine C, right? The set of all functional dependencies logically implied by F is a closure of F. We denote closure of F by F plus. F plus is a functional dependency set, okay? We find F plus applying the Armstrong exams. For example, if alpha and beta, if you consider, then beta is a subset of alpha, then alpha determines beta, of course. So then if alpha determines beta, then okay, any constant into alpha, constant into beta, it can be determined. That is called as an argumentation. Then if any alpha determines beta, then of course alpha and beta can determine any of the constants, that is transitivity. Alpha also determines y, beta also determines y, okay. These rules are sound. It means generates only functional dependencies that actually hold and complete. It means generate all the functional dependencies that hold. Okay, so how do you compute the functional dependency? That is a closure computational functional dependency. The closure computation is nothing but, so initially functional dependency we are assigning to that, and we repeat for each functional dependency in a small f in a capital F plus, applying the reflexivity and argumentation rules on F. Okay. So what does reflexivity and argumentation we have seen in the previous slide. Okay. Add and the resulting functional dependency to the F plus. Whatever the functional dependency we are getting, then you can add it to them. For each pair of functional dependencies F1, F2 in F plus, if F1, F2 can be combined using the transitivity, then add the resulting functional dependency F plus until F plus does not changes any further. We shall see the alternative procedure for this task. Okay, like a closure of functional dependency. So we can further simplify the manual computation of F plus by using the following rules. One is a union. Union, it says that if alpha determines beta and holds alpha determines y, that holds, then alpha determines beta and y, right? Of course it's a union. Then if alpha determines by, then we can say alpha determines b as well as alpha determines y. That is what the decomposition. Then if alpha determines beta, holds any constant into beta determines gamma, holds, then alpha gamma determines a particular symbol, that is a sigma, holds a pseudo transitivity. The rules can be inferred from the Armstrong exam. That is, C is extraneous, AB determines CD, since BC AB determines C, can be inferred even after deleting the C. Okay, so how do we test in attributes? So consider a set of F functional dependencies and functional dependency alpha determines beta in a F. To test if attributes A belongs to alpha is extraneous in a alpha, then compute the alpha, that is a minus A plus, using dependencies in a F. check that alpha minus capital A contains beta. It does not A extraneous in a okay. Then for testing the attributes belongs to A belongs to beta, that is extraneous in beta. Then compute the A plus using only dependencies in F dash, that is F determines alpha determines beta as well as alpha determines A minus beta. So check out alpha plus transitions if it does extraneous beta. Then what does the canonical form for this? A canonical cover of for a set of dependencies Fc such that where F is logically implies on all the dependencies in Fc, then Fc is logically depends on in F, and no function dependency in a Fc contains extraneous attribute, and each left side functional dependency in a Fc is in. To complete the canonical cover for F, repeat, use the union rule and replace by dependencies in F. Alpha 1 to beta 1. Then alpha 1 determines beta 2. If this is the case, then of course alpha determines beta 1 and beta 2. Find the functional dependencies like alpha and then with the extraneous attribute either alpha or beta. Okay. So then if an extraneous attribute is found, delete from alpha to beta until F does not change, function dependency does not change. Okay. So then this is the example. A here having a 3 columns A, B, C. Then A determines BC, B determines C, A determines B. Then AB determines C is the canonical form. As you can see, the combined A determines BC, A determines B, and A determines BC. Set is now like A determines B and A determines C can also be written as. Okay. And then A is the extraneous in AB determines C, that is check if the result deleting from A from A, B to C implies the other dependencies such as yes, in fact B determines C is already present. Then set now A determines BC, so BC determines C. Extraneous algorithms are check if A determines C is logically implied by A determines B and other dependencies. Yes, using a transitivity, A determines B and B determines C. You can use the attribute closer to of A and more complex cases. Okay. Then lossless decomposition for a fourth normal form, multi-value dependency. Okay. Whereas lossless decomposition, for example, in case of R1 and R2, we require the following postulate relations. That is, projection of R1 from the relation R, projection of R2 from the relation that determines the two tables. Then R1 intersection to R2 is nothing but R1 only. R1 intersection to R2 is nothing but R2 only. Okay. Then we have R is nothing but ABC. A determines B, B determines C. Then this is for transitive composition. The lossless decomposition is there are two relations R1 and R2. A determines B and B determines C. Okay. And then R1 is having the AC also. So lossless decomposition, it means while a union A and A determines AB is not dependency preserving. So check out B with the C without computing A1 and A2. Let Fi be the set of dependencies and F plus that includes the only attributes in a array. Decomposition is dependency preservative if F1, F2, so on, F3, Fn is equal to F plus. If it is not, then checking the updates for the violation of the function dependency may require computing joins, which are expensive. To check if dependency alpha to beta is preserved in a decomposition for R and R1, R2, so on up to Rn, we apply the following test. Okay, so whereas C is equal to alpha, then result changes to do. Yes, of course, the result is null. If the result contains all the attributes in a beta, then functional dependency is preserved. We apply the test on all the dependencies in a F to check if the decomposition is dependency preservation. So this produces the task polynomial time instead of exponential time required to compute the F plus and F1, F2, so on, F2, Fn is a set. For example, here is an example: A determines B, A determines B determines C. Then A can be a transitive dependency. It is not a BCNF. A decomposition like R1 and L2 can be taken place. That is what R1 and L2 together can perform a BCNF, lossless joint decomposition dependency preservation. So while testing the BCNA, that is to check if now non-trivial dependency alpha to beta because of violation of the BCNA. First one, what you have to do? You need to compute the alpha plus the attribute closure of alpha and verify that it concludes all the attributes in a capital R. That is the always super key of R. Simplified test to check if the relation schema R is a BCNF. It's supposed to check only the dependency in a given set of F for violations BCNF rather than the checking all the dependency in a F plus. Okay. If none of the dependencies F causes the violation of BCNF, then none of the dependencies in a F plus will cause the violation of BCNF either. However, using only F is incorrect. When testing a relation in a decomposition R, consider the relation consists A, B, C, D, E, and the functional dependencies are A determines B, BC determines D. Then decomposition R into R1 says that neither the dependency in F only attributes from the ABCD, so we might be misled into thinking of R to satisfy the BCNF. In fact, dependency is a F plus shows the R2 into not in a BCNF. Then to check the relation Ri, decomposition of a R is a BCNF. Either test Ri BCNF is respect to the restrictions of a F to R, then F plus that contains the only attribute from Ri. Okay. So this is the algorithm which we are using for the BCNF decomposition. That is R. Then yes, suppose false, it's computed F plus. While not done, if there is a schema Ri in the result, that is not a BCNF, then we okay, any alpha to beta non-trivial function dependency that holds on a R such that so alpha is determines Ri is the not F plus. Okay, so that is the case. So you can perform any set operations like union and intersection minus, else it will be true. Okay, so then original relation R and a functional dependency F. R is the branch name, branch city, branch asset, customer name, customer loan number, branch name and city. Okay, loan number, amount. Okay, to perform these two, you need to combine the table first. Then key is nothing but together we can depend on a key. Then decompose nothing but R1, R2, R3, right? And then R4. So each branch name provides city and asset. So then customers are going to be loan for one customer name, loan number. Final decomposition is alpha 1, alpha 2 and alpha 4. Whereas BCNF and dependency preservation, it allows possible to get the BCNF decomposition, that is dependency preservation. Yes, R has these many keys and F has. So whenever you perform a L determines K, or K is identified by L. Then two candidates P, JK and L. Yeah, R is not a BCNF, so decomposition of R will appear. Okay. Third normal form. There are some situations where BCNF is not a dependency preservation, and efficient checking for the preservation, that is evaluation on updates is important. Solution is BCNF. Define a weaker normal form called as a third normal form, so which allows the redundancy with the resultant problem. We also view or see the examples later, but the functional dependencies can be checked on individual relationships without computing. There is always lossless join, dependency preservation and decomposition. Okay. So then rules we are having. In the first example, relation R. R consists JKL. So JK determines L. Then L determines OK. So K, this is what the case we are having. That is, these two candidate key whenever having a JK and a JL will be in a relationship. Okay. So redundancy in a 3NF. There is some redundancy in a schema. So you can see here. The repetition formation, for example, relationship is nothing but R1 and K1 need to use a null values, for example, representation of a relationship. Okay, optimization need to be check only the functional dependencies in a F and need to check all the functional dependencies in F. Use the house attribute closure to check for each dependency alpha to beta if alpha is a super key. If alpha is not a super key, we have to specify of each attribute in a beta containing a candidate key of R. This test is rather more expensive. Nice, it involved finder candidate keys, and testing for a 3NF has been to be NP hard, and testing decomposition into third normal form is nothing but testing of polynomial type. Okay. Then let F be the canonical form of F, that is I is equal to 0 for each functional dependency alpha to beta in FC. Though if some of the schema Rj contains a lesson from particularly, then I is equal to I plus 1, and then Ri is equal to particular alpha and beta. If none of the schema Rj lies between 1, J and I, constituent a candidate key for R, then it begins I is equal to I plus 1, and then any candidate key for R, so any one key you can return. Okay. So 3NF is the above algorithm ensures that each relation schema Ri is 3NF, and decomposition using dependency preservation and lossless join. Proof and correctness is at the end of this presentation. Yes, okay. Then relation schema, one of the example is set of attributes are defined in relation schema. Then functional dependency of this relation schemas are is customer ID, employee ID and customer ID, where it represents employee ID on a department name, then branch name and employee ID. We first compute the canonical cover. Branch name is extraneous in the RHS of the R1 dependency to neither it always possible to decompose a relation into a set of relations that are in 3NF. Okay, the decomposition is lossless and decomposition is preservation. Okay? So preserved. Similarly, you can say in a 3NF, and BCNF is nothing but it's a BCNF, that is the decomposition is lossless, and if not possible, it's preserved dependency can be done. So any questions? Yes, here is one question that form a relational database possesses that the individual entity, that is a C4NF. Okay. Then comparison between the BCNF and 3NF has over already. So employee department 1 has these many fields in it. For any pin code there is only one city and state. Also for a given street and state there is a source. Just one pin code is normalization of S terms EMPTT and then is in a relationship. For example, 1NF only, 1NF is also called as 2NF, 3NF is also called as 2NF, and 1NF3, 1NF video. BCNF, hence the relations are nothing but 3 to 1. Okay. This is what the that is totally functional dependency are going to be preserved in this one. Yes, these are the references which I have used for my video class. Thank you.